So this is here. This is highest. I'm going to say BP for boiling point. So highest BP to lowest BP. And then we're given the following items. So I'm gonna write this in blue. So we're given paraffin. We're given butane, octane, 2,2,4 trimethylpentane, and then we're given octadecane. Okay, so let's look at these ones here, and let's look at the structures of this. So for paraffin, this is a common name. So I'm just going to I'm going to search up what the structure of this one is, because I don't know what the structure of the common name of paraffin is. So let's look at paraffin, and let's look at the chemical structure. So paraffin, I'm guessing it's this one here, and I'm looking for chemical. This is the chemical structure here. This is C31H64, and it looks something like this here. This hydrocarbon is C31H64. So let me write so paraffin here is C31H64. And octadecane is actually not an IUPAC name here. So I'm gonna have to look up what the structure of octadecane here. Octadecane is C18H38, right? So this here is probably not something you learn in grade 12. Octadecane is 18 carbons in chain. So it's H18, I guess this would be 30. This is 38, right? H18, H38. Yeah. Okay. Okay. So what we have here is we have these two compounds, and we know butane, octane, 2,2-methyl pentane. So let's draw these out. So paraffin and octadecane I'm not going to draw because these are very big structures. But butane, what we know is this here is a line diagram for butane. Octane is simply just 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. And this is 8. 1, 2, 3, 4, 5, 6, 7, 8. And then 2,2-methyl trimethylpentane. So I have a pentane here, and then 2,2-methyl. So I have a methyl on 2, and another methyl on 2, and then methyl on 4 as well. So this would be here. So it's here 1, 2, 3, 4, 5 is our 2,2-methyl, 2,2-trimethyl pentane. So we have all these ones, and it's telling us to rank them from highest to lowest BP. So according to, again, we don't have, in terms of, let's look at our intermolecular forces. When we're talking about our highest boiling point and what affects boiling point is our intermolecular forces. In this case, we have all hydrocarbons, so we're all looking at the chains of hydrocarbons. So all these guys here are all alkanes, right? They're all alkanes, and they're all hydrocarbons, right? So they're all aliphatic chains. So basically, the only thing that affects BP here is the London dispersion forces, right? London dispersion forces. We don't have any dipoles. We don't have any hydrogen bonding here. So the only thing that affects these guys are the London dispersion forces. And as we know, London dispersion forces, the higher the I'm going to say LD forces, the higher the BP, right? So it's proportional with our BP here. So when we talk about London dispersion forces, what are London dispersion forces? Well, these are the forces that kind of increase as the size of the chain gets bigger, right? The bigger the molecule, it's harder for us to break up or to boil our hydrocarbons. So in this case, obviously the biggest compound would be the hardest to break up, right? So in this case, paraffin is our biggest compound, right? C31. So the highest BP would be paraffin. The second biggest one here is octadecane because it's C18H38. So octadecane would be next. And then we have next we have butane, octane, and 2,2,4-trimethylpentane. So let me just count the carbons here. We have 1, 2, 3, 4, 5, 6, 7, 8. So in this case, this has the same number of carbons as this. So octane and octane would be the same boiling point as 2,2,4 trimethylpentane, and then we have butane as our lowest BP. So when we talk about octane versus 2,2,4-trimethylpentene here, I would actually say octane is actually slightly would be slightly increased in BP, even though they have the same carbons, because it's a straight carbon chain, so it's a bit harder for us to break that chain here. Whereas 2,2,4-trimethyl might not be, but these are very much similar in BP. So let's look at the answer here: paraffin, octadecane, octane, 2,2,4-trimethylpentane, and butane. So this here is correct. Solids have higher, is good. Branched chain hydrocarbons have lower boiling points than straight chain isomers, right? So when we're talking about octane and 2,2,4-methylpentane here, branched chains have lower boiling points than octanes, and that's what we talked about before, right? Just because an octane, if it's a straight chain, it's much harder for it to break, whereas if it's that branched hydrocarbons, sometimes maybe we can break like a methyl here and a methyl here, so it's slightly lower, not very much, but slightly lower. So in this case, this here is correct here. And I say here, octane is a straight chain, whereas isomeric 2,2,4-trimethylpentane is a branched chain. So between that, octane would be the same here. So maybe it's not even, it's almost equal. I would say almost equal, but I would say it's almost equal to, but it's not yet. So it differs very slightly, and you can see here 125 and 99 degrees is pretty slight change here. So this here is a perfect solution, and great logic here. So this here is correct.